Continuing with section 1.1, now we will learn how to solve the system of linear equations. In the first video of section 1.1, we saw that a system of linear equations can be represented by an augmented matrix. We also learned the three operations or row operations that can be applied to any matrix. And the first of them was interchange or swap. So interchange, so what that means is that we can interchange any two rows. So we can make the first row actually the third row, and then third row becomes the first row. Or we can swap the first and the second, or second and the third, or so on. So whatever is required. Second thing was scaling. Scaling means that you can scale a row, means you can multiply a row by any non-zero constant. So you are not allowed to multiply by 0, but you can multiply by any other number, negative, positive, fraction, decimal, anything. And the last one was replacement. So replacement means that you can replace a row by adding in that row a multiple of some other row. So remember, the row that you are to which you are adding a multiple is going to change. The other rows will stay the same. Now, two matrices are called row equivalent if there is a sequence of elementary row operations that transform one matrix into the other. So another way of saying is that if one of the elementary row operations is applied to a system, the resulting system is equivalent to the original system. Now note here, if the augmented matrices of two linear systems are row equivalent, then the two systems have the same solution set. So this is kind of repeating the same thing that we had before. Now the question here is, main question in this section is that is there a solution? Is the system consistent? Remember, system will be consistent when there is a solution, at least one solution. And what are our possibilities? We saw again in video 1, we saw that a system of equations can have three choices. It can have a unique solution, it can have infinitely many solutions, or it can have no solution. So if it has one solution or infinitely many solutions, it is called a consistent system. So that's what we want to check. Is there a solution? And if there is a solution, second question, so this is about for the existence part of the question, existence. Does the solution exist? And then uniqueness. So this is about uniqueness. So if the solution exists, is it the only one? That is the solution unique? So these are the questions we will be answering for the upcoming examples. So let's dig in. First example, solve the linear system. Basically, in all cases, we have three cases. One will have a single solution, infinitely many solution, and no solution. So we have this system. This is actually the same that we have been working with earlier. So we start by writing the augmented matrix. So the first row will be 1, -2, 1, 0. Now I'll tell you one thing. First, let me write this matrix: 2, -8, 8, and then 5, 0, -5, and then 10 here. And what comes here? 0, because the term is missing. Now, in many books, they draw a line here and keep it in all the matrices. This kind of to differentiate that the numbers on the right are the numbers which are to the right of the equality sign in the equation, and the numbers to the left are basically the coefficients of the variable. So the first column containing 105, these are the coefficients of the variable x1. Second column containing negative 220 is the coefficients of x2, and 1, -8, -5 are the coefficients of x3. But in our book, they don't use this line, so it's up to you. If you want to use it, good. If not, then you may. So it's okay, as long as you remember that these are the last column represents the numbers on the in the equation form. It's numbers on to the right side of the equality sign. Okay, so now what is the idea now? The idea is this, that if you have a square matrix, let's say you have a square matrix, so we want to have the matrix to be like this. Let's say I'm making a 3 by 3 matrix. So there will be 9 entries in it. You know that there will be 9 entries in a 3 by 3 matrix. So this is a kind of a square. You can see that. It has two diagonals. One goes like this and the other goes like that. So we are not interested in this one, but we are interested in this diagonal. So you can see these three values are lying on the diagonal. Too many values over here, looks like. Okay, so this is the main diagonal. We call this the main diagonal. And what these solid dot represents numbers. Could be any number, 0, positive, negative, anything. But the numbers over here numbers below the main diagonal must be 0. So this should be 0, this should be 0, and this should be 0. So we have 0, 0. So if you notice here, so we saw square here, but now you can see the triangle. So all these numbers, they can be any number, but the condition is that everything below the main diagonal is 0. All these values are 0. In a 3 by 3 matrix, there will be 3 of them. In a 4 by 4 matrix, let's see how many. So we have 16. And the main diagonal will be this. So all the entries below this must be 0. So which means this is 0. This is 0. And this is 0. And the same way, this one is 0. This is 0. And this one is 0. In a 4 by 4, we have 6 values that should be 0. And you can see so on and see. Now, for an augmented matrix like when we have, let's see where the diagonal is. The diagonal will contain these. This is our diagonal. So we want these 3 values to be 0 down here below the diagonal. The 2 of them are already 0. So maybe let's see what is our job here. Our job is to make this one 0. So this is a kind of a systematic method. So it's there is a path that it follows, and you must follow that path. You cannot jump around. Okay? There are first some things to do first, and those must be done first. So the first thing that we do is we kind of make everything that we need to make zero in the first column. So in the first column, one of the quantity we want zero is over here. That is already zero, so we don't have to worry about that step. The next is we want to make the entry in the third row of the first column to be zero. So we want a zero over here. So how do we do that? So we can get that zero here by using one of our elementary row operations. And how do we do that? Well, I cannot use, and if I use the second row, how can I use it? Well, I can swap the third row with the second row, but still it doesn't accomplish my goal. But what else can I do? I can multiply. I cannot make it zero by multiplying by anything because we are not allowed to multiply by zero. The only thing that, or the only choice remains is third operation, which was adding a multiple of another row to this row, third row. So what we are going to do in order to make it zero, so I have a 5 here. If I am adding, what should I add here to make it zero? Negative 5. So this is what I do. I will multiply the first row by negative 5 and add in the third row. So let me rewrite my matrix. And this is how we proceed. So I'll make a long line arrow here and write on top of it what I'm going to do. So I'm going to multiply the first row by negative 5. Let's say negative 5 R1 plus R3. So I'm going to multiply the first row by negative 5 and add it into R3. So what is going to change? Change will be R3. The third row is going to change. The first row is not changing. Okay, remember that you are not going to write in the first row negative 5, 10, negative 5, 0. That will be wrong. That means you are also multiplying the first row by negative 5, which you don't need to. So when I do this, my first row remains the same, whatever it is. The second row remains the same. The third row now changes. Now you should be able to do it in your head. If not, then you have to go somewhere on a scrap paper you can do, or you can make a line here and do your rough work. So here you can say, okay, when I multiply the first row by negative 5, I get negative 5, 10, negative 5, 0. And now I have to add the third row to it. So I have 0, 5, 0, negative 5, 10. So when I add them, 0, 10, negative 10. Now I can bring it here. So we are done. Now look what happened when we did this step, which was a necessary step, but we lost the 0 which was in this place, which needs to be there. So that's what our procedure tells us. Remember these 3 zeros? So this 10 needs to be a 0. So we could use any, of the 2 rows, first and second, to make it a 0? While if I use the first row, can you notice if I add a multiple of the first row to the third row, for example, if I multiply first row by 5, negative 5, no, 5, sorry, so I'll get negative 10, negative 5, I'm multiplying by 5, not negative 5, 5, negative 10, 5, 0. And now if I add third row, what is going to happen? I'm going to get this 5. What happened? We just made this quantity 0 and now it's become non-zero. Then I have to make it 0 again. So to avoid this, what we do not use the first row now, we will be using the second row. But before I do that, let's simplify things here. So you can see we can easily divide, multiply, sorry, we don't use the word divide because that's not in our 3 allowed operations. We can multiply the second row by 1/2. I can write it like this, 1/2 R. And also we can multiply the third row by 1/10. We can do these 2 steps in one go. Did I do anything to my first row? No, nothing, so it will remain the same. The second row will become 0, 1, negative 4 and 4. And the third row will become 0, 1, negative 1 and 1. Okay. So now what to be done? So now you see we have these 2 zeros. We want this quantity to be 0. We want this to be 0 here. So I will use the second row to make it 0. I have third row, so I am going to add multiple of the second row to the third row. So which multiple? Well, because I have 1 and 1 here, so I need to have one of them to be negative, which is this second row. So negative are 2. So I'm multiplying the second row by negative 1, and then I'm adding it to the third row. So what do I get? Okay, which row got changed? Remember R3. So the first row will remain as it is. Second row will remain as it is. Third row. So I multiply the second row by negative 1. So this quantity becomes negative 1. I add it in here so that this was already a 0. Now when I multiply the second row by negative 1 here, so I get negative 1 times negative 4 is positive 4, and then I have negative 1. 4 minus 1. So I have 3, and then I have 4, negative 4 plus 1. So I have negative 3. So we have that form. This is called by the way, this is called the upper triangular form. Upper triangular form, where all the elements below the main diagonal are 0. Now, can there be zeros in this upper piece of the triangle? Yes, you can see there is a 0 here. Can we have zeros along the diagonal? Yes, but at least one entry in the diagonal must be non-zero. Okay, so after we get here, now we can do something we call back substitution. For that, you need to go backwards and rewrite the equations that correspond to this system. So let's write the equations. The first one, remember these are the coefficients of x1. The second column gives us the coefficients of x2. Third gives us the coefficient of x3, and these are for the value b. So first row gives us the first equation, so x1 minus 2x2 plus x3, 1 into x3 is just x3 equals 0. And the second equation gives me x2 minus 4x3 is equal to 4. And the last row gives me 3x3 equals negative 3. So now you see again this is also like upper triangular form. We can start from here. So we get from this equation, we get x3 equals negative 3 over 3, which is negative 1. So this gives us x3 is negative 1. Now we take this value and substitute in the, so this equation gives us, so this one gave that, or this one is giving me x2 equals 4x3 plus 4. But x3 is negative 1, so I substitute that, and this gives me 0. Now from the first equation, we can get x1 equals 2x2 minus x3. Plug in 2 into 0 minus negative 1. So it is 0 plus 1, what? 1. So we have x1 is equal to 1, x2 is equal to 0, and x3 is equal to negative 1. And so each variable has only one value. So this means we have a unique solution. Or you can say exactly one solution. And then we have the system is consistent. So consistent system. And how do we write our solution? So the solution is, we write it as a triplet or tuple. That's what tuple is, 1, 0, negative 1. And now if you want, you can go back and plug these values in each of these three equations, and it must satisfy this equation. So this is how we solve use the augmented matrix to solve the problem. Let's look at the second one. So here is the system. We start with the augmented matrix and we apply the same technique that we just did. So we have 0, 1, 4, negative 5, first row, 1, 3, 5, negative 2, and then we have 3, 7, 7, 6. Okay. So remember our diagonal is first entry of the diagonal must be a 1 or a non-zero number. So what I can do, I can swap the first row with the second row or with the third row, it doesn't matter. Let me do it with the second row because it will be easier that way. So we say R1, double arrow, R2. We are swapping or interchanging first and second row. So second row is 1, 3, 5 minus 2. That becomes the first row. And the second row, the first row becomes the second row. Third row stays as it is. Again, we follow the the process exactly. So what we do in the first column, we have to have those 2 zeros. So the first 0 is already, one of the zeros already in that column. We don't have to worry about that position, but we have to have this 3 in place of the 3, we have to have a 0. So how do we get that? As explained before, by using the one of the properties of one of the operations we have learned. So I will multiply the first row by -3 and then add into the third row. So what is going to change? The third row is going to change. The first and second will stay the same. So what will the third row become? Well, think it. So I am multiplying the first row by 3, -3. So -3 plus 3, 0. Then when I multiply the next quantity, which is 3 in the first row, multiplied by -3, we get -9 plus 7, -2. Then 5 being multiplied by -3 gives me -15 plus 7, so -8. And then what else? With the last one, so -3 into -2, 6. 6 plus 6 is 12. So now our job is to make a 0 over here. So we can keep it like as it is and then add a multiple of the second row to make this quantity 0. So now you may now notice the pattern. So in order to make these zeros, the zeros in the first column, however big the matrix may be, however many entries may be down here, you will use the first row to make these entries 0. And in the second place, or the second column, you will use the second row to make the entry 0. And so on. So now, as I said, I can just multiply the second row by 2 and add it in the third row and make a 0 over here. Or I could multiply the last row. I could multiply the last row, third row, by -1/2. Okay, let's first do the replacement. So I'm going to multiply the second row by 2. I'm going to add in the third row. First row remains the same. Second row remains the same. Third row is going to change, but this will not change because we are just going to add 0 into 0. 0 plus 0, which is 0. So then I multiply by 2, second row, and add the -2, so I get 0. Then I multiply -4 by -2, I get -8. Sorry, we are just multiplying by 2. 4 into 2 is 8, 8 minus 8 is 0. And now 2 into 5 is -10, and plus 12, so we get negative. Okay, so we have the 3 zeros over here. Remember, this was our diagonal. Quantity below, and the numbers below it all are 0. So we have our form that we wanted. Now we do the back substitution. For that we need to write the equation. So this gives me the equation. Remember, this is coefficient of x1, coefficient of x2, coefficients of x3, and these are the values b. So that's why some books, they have a line, vertical line here. Some people use that, some don't. So the first one is giving me x1 plus 3x2 plus 5x3 equals -2. The second is giving me x2, 1x2 plus 4x3 equals -5. What is the last one giving me? So it is saying 0x1 plus 0x2 plus 0x3. What does that do? That gives me 0. and we're saying 0 is equal to negative 2. Now this thing is the culprit. Because it's wrong. This is false. So therefore we say no solution. Now when we say no solution, it means the whole system has no solution. It does not mean that x3 doesn't have a solution. It has to be that all all the x1, there is no x1, x2, because there should be x3, and since x3 we cannot figure it out, so there is no solution. And actually, even if we could, we could, there will be situations where x3 could be any number, but in this case, because we are getting a wrong statement or a wrong equation or a wrong result, therefore we say there is no solution. Okay, so I showed you the two cases where we have unique solution and no solution. The last one is infinitely many solutions. So let's see this example. What does this give us? So we start with the augmented matrix. What do I do? Then now you see there are nowhere we see 0. So we have to make this value a 0 and this value a 0. That is the first step. So in order to make the 2 a 0, I will multiply the first row by negative 2 and I will add it into the second row. So the change is coming in the second row. And then I will multiply. I can do these two steps in one go. That saves me, a bit of writing over and over. So I multiply the first row by 3 and add into the third row. So sorry, this was 2, right? In this case, we multiplied the first row by 2, negative 2, and then added into row 2. And now we are multiplying the first row by 3 and adding into row 3, and row 3 is the one which is going to change. So you can see from here, row 2 is changing, and from here, row 3 is changing. What about row 1? It will stay as it is. What happens in row 2? Well, negative 2 into 1 is negative 2 plus 2, so I get a 0. Negative 2 into negative 2 is 4. 4 plus 1 is 5. Negative 2 into negative 1 is 2. 2 plus 3 is 5. Negative 2 into negative 2 is 4 plus 1, 5. Okay, what about third row? The 3 into 1 is 3. 3 plus negative 3 is 0. 3 into negative 2 is negative 6. Negative 6 plus 1 is negative 5. Negative 1 into 3 is negative 3. Negative 3 plus negative 2 is negative 5. And then last one, negative 2 into 3 is 6. Sorry, 3 into negative 2 is negative 6 plus 1, negative 5. The next step is to make this quantity a 0, so we can just add the second row into this. I'm going to do R2 plus R3. Not again, this is the row that is changing, so I'm putting it at the end. What about the first and the second row? They will stay the same. When I add them, you can see these all become 0 in the last row. Okay. So do you think if I, at this stage, if I write the equations, we will get a something, a statement that is false? No. Why? Because the last row will now give us 0 is equal to 0, which is a correct statement. Anyhow, just to simplify the numbers, so that when I do the back substitution and I have simpler numbers, I will multiply the second row by 1/5. The first row remains the same. Second becomes 0, 1, 1, 1. The last row is 0, 0, 0, 0. So remember, our diagonal was here, and everything below the diagonal is 0. Okay, now let's write the equations. So I have x1 minus 2x2 minus x3 equals negative 2, and then second row gives us x2 plus x3 equals 1. So now you see we don't have like a number exactly that we can write, but this is what we do here. So we don't have like in the first example, x specific value for x1, x2, and x3. But if you notice, from the second row, I can write x2 equals 1 minus x3. So x2 can be represented in terms of x3. And from the first row, x1 will be equal to 2x2 plus x3 minus 2. Now I will replace the x2 by this quantity that I just had, 2 times 1 minus x3 plus x3 minus 2. To simplify, we get 2 minus 2x3 plus x3 minus 2, and that gives me minus x3. So what did we notice? Well, it means x2 and x3 depend on, x1 and x2 depend on x3. And what we do now, we say that there is x3 is a free variable because it has no restrictions. So we have x3 is an independent variable or a free variable. What does that mean? It means if you choose a value of x, for example, let x3 equals let's say 1. What does that mean? It means x1 will be equal to negative 1 and x2 will be equal to 0. If x3 is equal to minus 2, then it will mean that x1 is equal to 2 and x2 is equal to 3. So you can see that for infinitely many values of 3, so that's why we are getting infinitely many solutions. So the way we can write our solution is So remember x1 is equal to x negative x3. So negative x3 comma 1 minus x3 and then x3. Now this is called a parameter, and we say the other two equations are parameterized by the x3. Sometimes we say let x3 equal to some letter t, for example, then solution becomes negative t 1 minus t t. So this is how we solve or we write down our solutions when we have free variables. So in this case we had only one free variable. We can have more than one free variables, as you will see in coming chapters. Okay, so this is section 1.1.